Thank you all for joining this webinar. I'm Nabil Mancheri, a senior advisor at the EIT Raw Materials. As many of you may have known me, I have recently joined EIT Raw Materials. I'm not going to explain. I think you are well aware of what is EIT Raw Materials. But before I go to the webinar topic, I want to introduce you to something new that EIT is launching. That's very relevant to our sector, especially on rare earths and magnet. So EIT is going to soon launch for strategic impact groups, or more maybe for networks on rare earths and magnets. We call it SIGN, and battery materials, then we call green metals, and mining and processing technologies. Basically, what is intended of these four strategic groups are, we will tackle four critical pillars to accelerate European industrial competitiveness in the sectors like skill shortage, innovation gap, investment shortfalls, and regulatory challenges. And so the first to SIGN on rare earth and magnets and battery materials, we will launch in April 9 and 10 in Frankfurt. So as you are all part of the rare earth stakeholders, I would like to invite you to join us in Frankfurt on 9 and 10 April. And we will have workshops around this topic I mentioned before. Now I go to the Magellan. Magellan is a European Horizon 2020 project coordinated by Orano, which is a well-known company in the rare earth field. And the project ultimate aim is to kickstart the creation of a new value chain for permanent magnet recycling and manufacturing in Europe. And the solution is that Magellan aims to develop and demonstrate in an operational environment, TRL 7, a novel and cost-competitive, environment-friendly solution leveraging functional recycling, highly advanced process for manufacturing permanent magnets, and new designs for EVTMs. And different work packages look into the whole value chain, and we have specific members looking at this. We have 14 consortium members from all over the Europe, led by Orano and EIT Raw Materials as well, and CEA, magnet companies like Magnet-T, and EIT Raw Materials is also part of the consortium. And so this webinar is a series that we had the first and second one in previous month, where we looked at the different aspects of recycling permanent magnet issues. And this webinar also on recycling, but we will closely look at the economic and technological challenges, and also looking at what we usually call is short loop and long loop to process route for recycling permanent magnet. So I have expert and companies, they are well known in the industry and in our sector, and they will provide an update and discuss the issues. So the first speaker is from Sorana Luco. She is from CEA. She is working on the Magellan project itself, and she is the next speaker. She has several years of experience in the industry in the field of material science and material science synthesis, characterization, magnetic materials, semiconductors, and ceramics, etc. She did her PhD in material science in 2022 in France, in Grenoble. And her area of expertise include experimental synthesis and characterization of rare earth intermetallic alloys and compounds, as well as recycling technologies by powder metallurgy. So the first presentation is by Sorana, and the floor is yours, Sorana. Maybe you can share screen Yeah. Please start.
Okay, yes.
Yeah.
Thank you, Nabil. I will share my screen now. And you just tell me if it is okay for everybody. No.
Yeah.
Okay. Well, thank you, Nabil, for the introduction. And I want to thank to the organizer for inviting me to present the short loop recycling strategies for the neodymium iron boron permanent magnets. So as Nabil said, I am a researcher in CEA in Grenoble, and I work mainly on the my research field is mainly on the permanent magnets. So I will start by introducing some context about the magnets, the challenges and the opportunities. I will briefly present the existing recycling strategies, and I will make an overview on the research and development program that we have together with Orano and the value proposition. And after that, I will focus the presentation on the short loop recycling routes. And of course, I will conclude the presentation. So the low carbon and circular economy is a necessity for the energy transition, and the permanent magnets are key components for the low carbon economy. Among all the existing permanent magnets, the neodymium iron boron are the world's most powerful and efficient magnets, as you can see in this graph. And they are used at about 80% in the electric vehicle traction motor technologies, and a large part of the offshore wind turbines also use this kind of magnets. The global demand of this material will increase in the upcoming year, and this will induce a high supply risk for the permanent magnet. Europe considers its external dependence on permanent magnets as critical because China dominates the entire value chain of the permanent magnets, from the ores, the mineral extraction, the separation of the different rare earths, the metal conversion, the manufacturing of the alloys for permanent magnets, and manufacturing of the permanent magnets. Meantime, Europe imports almost all its need in permanent magnets from China. So a smart circular economy can meet the resilience challenges of the European energy transition. And we all know that permanent magnets are recyclable, and the recycling of this material becomes strategic. There are several recycling strategies. We can recycle these magnets by a very short loop, if I can say, the direct reuse, which is the most energy efficient strategy for the recycling. But the system where the magnets, they will be reused, should be compatible with the end-of-life magnets, and also we have to properly extract them from the end-of-life system. The short loop recycling, which is a metallurgical process, and I will detail in the next slides, and the long loop recycling, which is a chemical process where the rare earth elements, together with the other elements of the magnets, are extracted and can be used in various applications, including permanent magnets. But what we have to know is that short loops and long loops are very complementary. In this context, here we launch a research and development program together with Orano, which aims to industrialize and manufacture Recycled permanent magnets, high performance magnets, which incorporates at least 25% of secondary raw materials in a short loop process. The magnet recycling industry can capture growth opportunities in this strategic segment because stock of used permanent magnets is building up with significant volume of the first series of clean technologies. And Europe recognizes the strategic nature of permanent magnets recycling within the Critical Raw Material Act. So concerning the short loop recycling processes, the short loop recycling processes signifies that scrap magnets can be introduced in the different steps of the manufacturing of the magnets. So the high performance permanent magnets are manufactured by the conventional powder metallurgy route, which means that we fabricate an alloy by strip casting. This alloy is pulverized, the powder is compacted, then densified by sintering. An annealing heat treatment is applied to enhance the magnetic performances. Then magnets are machined, are coated, and then included in a system where generally we magnetize the magnet. In the short loop recycling process, so as I said, we introduce the scrap magnets at the different steps of this process. The melting route, or magnet to alloy also, we can call it, the scrap magnets are introduced in the casting alloying of the material, and in the powder route, we introduce the scrap magnets in the pulverization of the material. Concerning the melting route, it is performed by strip cast process. The strip cast process is a well-adapted and proven technologies in the conventional metallurgy process of the manufacturing of neodymium iron boron high-performance magnets. The raw material is induction melted. The melted alloy is poured on a copper water-cooled rotating wheel. And alloy under the form of flakes of several hundred of micrometers are obtained, and these flakes have a particular microstructure which is very well adapted for the subsequent steps of the manufacturing process. And only the strip cast process allows to obtain this particular microstructure. So in the melting route, the scrap magnets can be used as raw materials to fabricate alloys and subsequently magnets. This route is particularly interesting in the case of heterogeneous batches of end-of-life magnets, and especially highly contaminated in oxygen and carbon, and allows to avoid the conversion oxide to metal process. However, homogeneous batches highly contaminated in oxygen can also be recycled by this route. So this process is versatile. Two kinds of scenario can be seen and can be used for this recycling process. And I will show you later some examples of magnets recycled by these routes. Here you can see some pictures of the strip cast equipment which is installed in CA-Li10, which enables to fabricate batches between 10 to 50 kilograms of alloy. Here we have the copper roll, rotating roll, and here you can see the melted alloy which is poured on this copper rotating roll. You can see in this picture an example of recycled alloy under the form of flakes with the particular microstructure that I I told you before, which is formed by magnetic dendrites of the magnetic phase, separated by very thin rare earth rich phase. And this particular microstructure is very useful for the next step of the manufacturing by the powder metallurgy route of the magnets. So here are some examples of recycled magnets, the results obtained within different projects. In the first case, some homogeneous batch of end-of-life magnets coming from wind turbine were used to fabricate alloys, and after that magnets. We can see that we have a very good recovery of the magnetic performances of the starting material using only the end-of-life magnets as the starting material to fabricate magnets. This project was financed by AET Climate. Another example is an heterogeneous batch of end-of-life magnets, where by a composition adjustment, we can meet the reference N38 state-of-the-art material. And these results also have been obtained within an AET raw materials finance project. What I did not say in the first case is that at the time of the project, the yield of the process was about 50%, but we have to know that oxidized material can enter in a long loop recycling process. So Magellan project, which is an H2020 project, its aims at developing and demonstrating in an operational environment a functional recycling route for the permanent magnets, which feeds into the melting route for the recycling of permanent magnets. So the recycled magnets are designed to meet the specification for the electric vehicle traction motors. As we can see here, the performances expected for these magnets. And the expected result is to increase the access of the electric vehicle traction motors industry to permanent magnets within Europe by improving the recovery rate of scrap magnets and by creating a new European value chain. It will be beneficial to European economies by lowering the supply risk for critical raw materials. If we talk now about the powder route, the scrap magnets will enter in the step of the pulverization during the conventional process to fabricate new magnets. And the powder route is based on the reaction of neodymium iron boron alloy with hydrogen. The powder route is particularly interesting from an environmental point of view. So the reaction of the neodymium iron boron alloy with hydrogen can be described here. Here we have some scrap magnets with the microstructure of the magnet with magnetic grain surrounded by non-magnetic rare earth rich phase. This alloy, these magnets, will react with hydrogen at ambient temperature. The reaction will enable to pulverize the material, and this reaction is called hydrogen decrepitation. This material, these powders, will have the same microstructure as the starting material. If we mill down this powder to fine grains, we can manufacture new magnets. Here are some examples of magnets manufactured with different load of recycled powder. And we can see we obtain good magnetic properties by this process. At higher temperature, under hydrogen above 600 degrees, the magnetic phase will disproportionate. However, this reaction is reversible because under vacuum, the neodymium iron and iron boron will recombine to form submicronic grains into a large particle. So this powder is coercive and can be used for the bonded magnet. Here you can see the microstructure of a particle and inside submicronic grains of neodymium-2 iron 14 boron. So in summary, the recycling of permanent magnets is possible, is necessary, and is strategic. The short loop and the long loop recycling strategies are complementary and each one is necessary. The short loop preserves value and strategic interests by producing magnets and offer environmental benefits, reducing greenhouse gas emission and water consumption. And I will finish my presentation by presenting you our pilot line, which is under installation in CEA. And the research and development program has a unique position to fabricate recycling magnets, which will incorporate at least 25% of secondary material from the short loop with a target to meet the performances necessary for electric vehicles, so high performance magnets. We also work on the advanced manufacturing process to fabricate net shape magnets. And this research program enabled us to build up the pilot line that is unique in France and rare in Europe. With some, here are pictures of some equipment installed in CEA. And thank you for your attention.
Yep. Thank you, Sorana. A great presentation, very valuable. And thank you for joining us. I forgot to mention that maybe people can, type their question in the chat or in the question answer section, tab. So, you now we will start with the next presentation. But meanwhile, if you have any specific questions, Sorana, you can type it there. And then our next, and we'll also, in the last half an hour, we will have a question answer session. So you can ask there. And even our next speaker is Professor Carlo Burkhardt. Carlo is the professor of Manufacturing Technology and Scientific Director at the Institute of Precious and Technology Metals at the University of Applied Science, Pforzheim University in Germany. And he's also served as a professor for materials at the Josef Stefan Institute in Ljubljana, Slovenia. And he's well known in our circles. He's also the coordinator of the EU Horizon project, Resilience, and also was the coordinator of its predecessor project, SUSMAGPRO. Professor Carlo has a PhD in metallurgy and materials from the University of Birmingham, which he acquired in 1996. And I also would like to inform you that Carlo also coordinates the standardization effort, especially with regard to CEN Technical Committee 472, which is the European Technical Committee on standardization of the rare earths and magnets. And Carlo coordinates the working group on labeling of the permanent magnet, which is one of the core issues in the EU Critical Raw Materials Act, and highly relevant not only to automotive OEMs and tier 1, but also to electronics, white goods, renewable energy, and medical equipment manufacturers. If you are interested in this, especially with the labeling of the permanent magnet in your product, I see people joining from different companies in our webinar. So it will be great in touch with this standardization effort, and that also align with our Critical Raw Material Act regulations. And Carlo, the floor is yours. You can start the presentation.
Okay, thank you very much, Nabil, for the very kind introduction. I couldn't have been better with a 472 in the labeling group. I also would like to point out that the convener of the technical committee, Michael Haschke, seems also to be in the audience. So if there are particular questions, I'm sure also happy to help. My topic today is also short loop recycling of rare earth magnets, but I should focus a bit more on a commercial point of view. As Nabil already said, I coordinated a SUSMEC Pro project and I'm coordinating the resilience. In SUSMEC Pro, we looked exclusively into recycling of magnets from 100% recycled material. In the short loop route, now in resilience, we look into a broader picture, which is mixing short loop material with long loop material and also with virgin material, preferably from non-Chinese sources. And I couldn't agree more with Sorana that these processes are complementary and they all have their advantages and disadvantages if you address the different let's say end of life streams. And just to clarify once again, the long loop means you go to a rare earth oxide, which means you split off the alloy into its chemical elements and go back to the rare earth oxide. Whereas the short loop is also called magnet to magnet or direct recycling, or we particularly in our bubble, we call it HPMS, which is a hydrogen processing of magnetic scrap. I will look into a little bit the environmental aspect a bit later, and would like to start first with another topic, which I think is a very important one, because we just heard that recycling of magnets is possible. Yes, this is true. However, the recycling rate still is very low, and there are various reasons. First of all, end-of-life magnets are not all neodymium boron. The majority of it is ferrites. There is also samarium cobalt, and even neodymium boron comes for recycling in two completely different states. One is polymer bonded, which is not so good to recycle. I'm not saying it's not possible, but it's probably commercially not very viable. And you have the sintered magnets, and of course that's for the moment the main target, how we can recycle sintered magnets. So first of all, you have to distinguish what's in your component. And as said, today we have no labeling, and so it's quite difficult to find out what kind of magnets you have. And I even had some recyclers that struggled by buying loudspeakers and thought they have neodymium boron, and it was just ferrites, and they didn't make a profit out of it. The second big problem field is that currently we have no design for recycling. Most of the magnets are deeply embedded. They're glued into the components. They're coated with various coatings that are not so good for recycling. So here also that's a second problem field where one should look at. And the third one is that we have completely underdeveloped recycling schemes right now. So there are a couple of placebo things, like you give back your smartphone. However, smartphone is probably one of the worst example how to recycle a magnet, because there are only a few grams in, there are a lot of other materials in, but in the end, the material value is less than €2. A lot of mixed scrap is ending in mixed deposits, and even a lot of it is exported. That's why I put this kind of provocative thing here. And as said already, the magnet content in the products is often very low. I mean, neodymium boron magnets are fantastic because they have a high energy product because of their performance, but it means on the other hand, you need only very little in a lot of components. So in a smartphone, we're talking about 4 to 8 grams if it comes up to it, and very deeply embedded. So you wouldn't recycle a smartphone just because of that. The next thing that's causing a lot of issues is that the current shredder processes, which are used for a lot of recycling operations, they are not suitable for recycling neodymium boron under various aspects. First of all, the magnets agglomerate. And this is also hated by the recyclers because it leads to downtime, it leads to increased wear of the shredding plates. And it's very difficult if you look here on the left side on this hard disk drive scrap, for example, to recycle something where the magnet is finally dispersed. And obviously, because of their hardness, they're brittle, they are breaking and they're agglomerating. And if you walk through recycling sites, you see a lot of spaces where a lot of magnetic scrap is agglomerated. And really, recyclers to date, they are not particularly fond of magnets. This shredding procedure, of course, is changing because in most cases where you have a neodymium iron boron magnet and the motor, you also have a battery pack. And these battery packs, they don't like to be recycled because of the oxidation. They can combust instantaneously. And there are a lot of fires all over Europe in recycling sites because of that. So more care is taken to separate things. And that's, of course, that's the good news for magnets. What we did in the SUSMEC Pro and Resilience project, we dismantled a lot of components where we could get hands-on just to see what kind of magnets are in. And we classified these products, first of all, for accessibility. And that's a very important thing, because if you look, for example, into the steering motor, you see up, I don't know if you see my mouse pointer or not, it's the upper left-hand corner. This has a material value of magnets of about 14 euros with current prices, but you need about 1 hour to access it, which in most of European countries is about 40 euros. So this is not a business case. So accessibility, how fast and how high is how fast you can get it out and how high is the effort to liberate the magnet from the component is essential for magnets recycling. Second is fixation. How are they glued? Can you easily demagnetize the material? How embedded is it? What kind of contaminations do you have? It's not only the glues, it can be spray paint, it could be polymer coatings. And the second set of parameters that we looked at are the magnetic properties. What kind of magnetic grades are in the respective components? And we set up a comprehensive database. And this database we use for two reasons. One is input for automatic disassembly and labeling, because for me, that's the key for magnets recycling to make it commercially viable. And the second, of course, is the other side, is input for design for recycling. Then in future, we avoid a couple of mistakes that cause us now trouble with automatic recycling. So in the next step, we looked into the major value streams that are now in magnets. And one of it is hard disk drives. A lot of people look at you a bit strangely and say, well, my laptop has an SSD. And of course, the consumer market is not the target. And here also the statistics lie, because they look only at the consumer market. But we have billions and literally billions of hard disk drives that are in server farms in the data centers. And with KI, this will increase again massively. So what we've developed in SUSMEC Pro was first, and that's a typical university project, the robot was for free. So we build everything around this huge robot. Here you have a sensor that's a direct box. You see a sensor which is detecting on which side of the hard disk drive the magnet is, and then this side is chopped off, and it then goes. The non-magnetic containing part is going to the shredder, and the rest is going into magnets recycling. What you see down here is if you should start video again, that's Evolution 2, that's the industrial machine. And if you look at the cycle times, it's 3 times as fast, and it's now much smaller. And this is what is going into the data centers when it's doing the automatic separation. So another value stream that we looked into is the flat screen TVs. Flat screen TVs, again, would have a magnetic content that's not viable for recycling, but you have to open the flat screen TVs anyway to get out the TFT screens because of the mercury. And then because they're open, you can extract easily the loudspeakers that contain the magnets. And here we have ferrites and we have neodymium iron boron, currently about 50-50 ratio. The flatter it is, the more neodymium iron boron will be in, so increasing with time. So this is a very simple separation mechanism that detects via visual control and some sensors what is a neodymium iron boron, what is a ferrite, magnet, separates it, and then it can go into recycling. A third thing we are playing on with is, of course, motors with embedded motors. You see here a machine that presses out the shafts. That's then doing a heat treatment of the rotor that's falling down, and then is separating let's move a bit quicker here, then separating the magnets from the electrosheets. All these things are IP protected, as is this hydrogen processing of magnetic scrap that has Sorana shown before, which is when you introduce hydrogen into the system. But the beauty of it is that not only this works for magnet, but it works for deeply embedded components. So you can put in the corner that we chopped off from the hard disk drive into the reactor, you tumble it, and during the hydrogenation, which you see here in this video, the material is not only forming a powder, it's also demagnetizing. And so by tumbling even complete rotors or corners of hard disk drives or parts of the loudspeakers, you can separate the magnetic material, and that makes it a very cheap liberation mechanism. And that's why we think that this has a very high potential. Again, this is IP protected, in this case by the University of Birmingham. Then what you do, if you have the powder, ideally you can take it, compact it in a field, sinter heat treat it, shape it, and coat it, and it's just mirroring how you sinter magnet from virgin material. And that also makes it very simple to blend in recycled material into new material with the same processes. Should have probably added here the powder treatment. Powder treatment means jet milling. You have to jet mill the material. And during the jet mill, you can also take out impurities that haven't been filtered before with a sieving. What has been done in a project and now also in a framework of commercialization, we can say more than 3,000 different magnets have been produced in the last couple of months, and we're in the middle of upscaling the processes. And you see everything that you see in green here. These qualities have been made from 100% recycled material. Important, not with added virgin material. With adding virgin material, you probably can push the boundaries even more, depending on how much recycled material you can put in. I personally see the future of the short loop either in the middle range. Yeah, there are a lot of magnets that are in the middle range, let's say between N35M and N40SH, where you easily can take recycling material if it's available, and not necessarily pushing the boundaries to these very high performance like N50, N52 with 100% recycled material. And here, of course, we will see in future blends that can take as much of the recycling material as possible. And that's one major focus of the Resilience project, to test out the boundaries, how much virgin and recycled material can be alloyed to get stable production of this kind of properties. If you look at the CO2 equivalent, what we've done here, and this was done by Enzo Granello, who is also in the call. He compared the LCAs and the TEAs that we made in the projects with a short loop recycling with literature. Which means with LCAs of primary material, of secondary material. And what you see here is a range, and the range is surprisingly large for primary material, between 21 and 89 kilograms CO2 equivalent per 1 kilogram of block of magnet. You see secondary, there are several around, say hydrometallurgy, pyrometallurgy. Reuse, of course, when you can reuse the magnet, that's environmentally the best. But you see that also the short loop recycling is very close to the reuse scenario, between 1.2, let's say, and 6.9 kilogram of CO2 per 1 kilogram block of magnet. And the differences are coming from the electric grid. The short loop recycling is very much dominated by the consumption of electricity. And for example, 6.9 in Germany means you use a mixed electricity grid, which includes some coal. In the UK, that's better because they have nuclear energy. And the 1.2 respective 1.3 is where you use 100% renewable energy coming from wind and solar energy. But you see what I've seen up here, electricity is a driving bit here. And then a bit of an outlook, and I've chosen here the German side. The UK side is 6 months advanced. But this is what we're currently installing in Germany. That is a plant that initially will be capable of processing around 100 tons of recycled material into sintered magnets. And in a second phase, which is already planned, and you see here the planning stage, we will go up to 500 tons, respective. The sister plant, being 6 months ahead, will be installed in Thaisley in UK, and another one with a capacity of 1,000 ton will be installed a year later in the US. And that brings me to the end, and the conclusion is short loop recycling is, from the scientific point of view, I think nearly at TRL 9. I mean, we're scaling up. The difficulties are in liberating the scrap. Here, HPMS can be helpful. It can be also helpful to feed some of the powder into the long loop. But a couple of things still remain to be solved in the next couple of months and years. And yeah, I'm open for your questions.
Yeah, thanks, Carlo. Very interesting and detailed analysis of the short loop process, HPMS especially. Before we move to the next speaker, we have a couple of questions, both relevant to you, Carlo and Sorana. Maybe, for other participants, maybe we can ask that question now. So first question maybe is, how you deal with this is maybe different ways, so both of you can answer this. What happens with the metals from the magnet coatings in the melting route? So that's the first question. Maybe you can answer, then I take the second one. And it could be also relevant to Patrick in the next presentation, and that I'll ask later, maybe because there are 3 different routes. Yeah, Carlo.
Well, in the melting, we're not doing any melting. So let's say what we're doing in HPMS. I mean, if it's nickel coatings, they're very easy to be sieved out because they get off in large flakes. If you have zinc coatings, the zinc coatings, they form very small particles. So they are kind of contaminate the magnetic material. So you have to be sure that you're below certain thresholds. I mean, zinc is not detrimental for the magnetic properties, but it can be during sintering because it's degassing and you have a vapor pressure. So this could lead to some pores. So we make sure with ICP, I mean, we're analyzing the material, that we make blends that are under a certain threshold. And a lot of the other material can be filtered out during jet milling via cyclones, and then also be wind sifted and reused. However, the quantities, one must say, are relatively small compared to the magnetic material. So it will be quite a while until, let's say, that there's a commercial value in these coatings in the nickel that you would sell off from the magnets.
So
Anna,
maybe
you want to add? Yeah.
Maybe I can answer about the melting route. So in the melting route, as Carlo said, zinc is not really suitable because it will evaporate. So it is important to remove it from the magnet. Nickel and copper coating can stay in the melt, and it will be contaminant elements for the magnet, but their share in the alloy is very little, is very small. So with a very little effect on the magnetic performances. If not, we can compensate if you mix virgin material with recycled material, you can adjust the composition to reduce at maximum the impact on the magnetic performances.
Yeah, thank you. And also a similar kind of question is that does the short loop recycling can also be for samarium cobalt and nickel?
The powder route, not currently. I mean, I probably forgot to say that neodymium iron boron disintegrates at room temperature with very low pressures. So you're in a range between 1 and 3 bar, usually a bit depending on the amount of heavy rare earths. But samarium cobalt will disintegrate at very much higher temperatures. So this is something I think currently addressed by research groups, not by us, so I don't really feel competent to talk about it. Our strategy is to eliminate all samarium cobalt magnets beforehand, because the magnetic powder of neodymium iron boron, even if demagnetized during the hydration, will stick still to the samarium cobalt magnets, and it would complicate the sieving and process very much if you would have to separate these two value streams. So we have to get it out before. This is why for us also the labeling is so important, that we don't have to go via sensors, but you would easily see in the beginning via DMC code, for example, that this has to be separated from the rest of the.
I agree with Carlo. Samarium cobalt does not decrepitate in the same range of process parameters as neodymium iron boron, and it's more difficult to use, for example, a powder route to recycle this kind of magnets.
Yeah, thank you. Then there are a couple of others that we'll take at the end of the session. So I invite Patrick Nee for the presentation. Patrick is the founder and senior vice president of Cyclic Materials, which is based in Canada. Patrick has a bachelor degree in mechanical engineering from MIT and a master degree in mechanical engineering from Tokyo Institute of Technology and an MBA from Columbia University. And Patrick, I'm not going to read your full profile. To save this time, you can start your presentation. And Patrick is Cyclic Material is looking at the long loop, and he could present what is long loop and what are the benefits and also challenges compared to the short loop. Thank you, Patrick, for joining us. Floor is yours.
Nabil, thank you very much. We're very happy to be invited by EIT Raw Materials to today's talk. Cyclic Materials is focused on producing a number of different metals for the energy transition, and the headline metals are the rare earth elements. We think we have the only scalable process for processing a wide variety of post-consumer recycling devices in local countries, so without having to use low-cost labor. And we're currently operating at commercial demonstration scale and shipping product to our next speaker, Solvay, every quarter. So our goal eventually is to be producing enough rare earth element raw material that if they were dedicated 100% to EV motors, so Tesla motors, for example, we'd be enabling the production of about 6 million additional motors per year. I won't go over this too much. Everybody's heard this 3 times already today. Magnets are made out of these rare earth elements. They're critical. They go into motors and a few other applications, which then enable trillions of dollars of applications downstream, from vehicles to data centers to robots to consumer electronics, etc. Really critical materials for our material world. We've already talked about the challenges as well with our ambitions for automobile electrification, wind turbines, upcoming robots. There's a growth in demand for these materials, and nobody wants a new mine in their backyard. So primary production is really having difficulty keeping up, and there's a projected shortage coming. There's a second challenge we've already mentioned as well. Most of these materials come from China. And so many of the governments and many industries are a little nervous about having all of their supply chain centered on these geopolitically sensitive area. So we believe that recycling of all types, short loop and long loop, can be a pressure relief to these challenges. But as we've heard, only about 1% of these magnets are recycled today for a very intuitive reason, which we've already talked about. Magnets stick to steel, and so they follow the steel into a steel refinery during any recycling process that exists today. Our goal is to raise that up to the 30–40% level. Why do we think that's achievable? Most other metals recycled somewhere in that 30–40, sometimes even 50% level. That's true for the base metals that we all think about, aluminum, steel, and copper, that even my mother could name, as well as niche metals. Vanadium, germanium hit these numbers as well. There's no reason that we as an industry, short loop and long loop, can't hit that 20, 30, 40% recycling rates for rare earths as well. So what we focus on is taking this range of feedstock on the left and producing these products on the right. We believe that there are very few opportunities where magnets are already removed from devices. If you're looking at end-of-life magnets, there's very few where they're already removed from devices, so you have to be able to handle an entire device. And as Carla was saying, these come in all different shapes and sizes, and even do have different types of magnets in them. Not only different types of grades, but the range of ferrite, neodymium, iron boron, samarium cobalt, and alnico. So we have focused on building a process that can take about 95% of all of these feedstock types through the same process. It's true if we ever get a General Electric halide, 15 megawatt wind turbine, that's just too large. We can't get that in. But our goal has been to build a process that doesn't need to differentiate between the different feedstock types. You take those devices, the first step is, how do you get the magnet out? And we're doing that in a way that also produces, because if you get a Tesla motor, you not only get the magnet, a device with magnets in it, but you also get copper, aluminum, and steel. So our process for getting the magnet out also allows us to separate copper, aluminum, and steel. And so those get sold into the local scrap market. These are graded materials that hit standard scrap industry grades. And so there's a wide and deep market for those. And they're critical to the economics. If you're going to obtain a Tesla motor, a scrap Tesla motor, the other buyers out there are buying it on those metal prices, copper, aluminum, steel. So if you don't get that recovery, you can't make the economics work. And then secondly, we get that magnet. That magnet then goes into a second step in our process, which is a chemical hydromet process. And our goal is to be producing rare earth oxides that are analogous to what comes out of primary mining. So we have a first process for separating a magnet, producing as a byproduct copper, aluminum, steel, and then a second process, which is a hydromet chemical process to reduce that magnet, which, as we've talked about, is an alloy, reduce that alloy back to its constituent raw materials. That supply chain that we're dealing with looks, as we see left to right. If you're looking at primary material, rare earth mining goes to separation, which goes to metallization and manufacturing the magnets, which goes into insertion of that magnet into a motor, insertion of that motor into an end product, gets used for 20 years if it's a car, gets used for 3 years if it's your cell phone, and that ends up in some type of recycling yard. And so these are the points where we are capturing material right now on the bottom. First of all, we are getting some material directly from magnet manufacturers. There is some physiological scrap rate when they're making magnets. And so we do capture material from magnet manufacturers. once you get into manufacturing of a motor or of a car, electric motors have been manufactured for 100 years. Scrap rates are relatively low. They're non-zero. We do recycle from manufacturing sites, taking their magnetic waste, again, in any form, still, depending on how, doesn't matter how far into the finished device it's been inserted, whether they're defective magnets that are still separate, whether they're in the rotor, whether the rotor's already been inserted into the stator, we can take it in all cases. And then that motor gets shipped off to a final assembly factory. Again, maybe that's being tested and it's found to be off spec, or somebody drops the motor. So we get some leakage through manufacturing on that bottom line. But the vast majority of the material that we source comes from end of life, and that is through a recycling yard. Now you're thinking, Teslas haven't been around all that long. Cars live 15-year lives, 12 years, 13 years in North America, 16, 17, 18 years in Europe. Are you seeing any Teslas yet? Not a huge amount, but we're seeing lots and lots of hybrids. Prius was introduced 30 years ago, and so there's plenty of supply of hybrids. And as you saw on the previous page, we're sourcing electronic waste, medical waste, wind turbines as well. These materials go through that two-step process that I talked about in the previous slide. And our end product is mixed rare earth oxides, or in our case, we call them recycled mixed rare earth oxides. About 85% post-consumer recycled and 15% in post-industrial recycled materials. Our flow sheet stops at mixed materials, and we provide that downstream to separators, which Lana will speak about next from Solvay. They're the ones who are doing the next step to get that material back into the supply chain. I think we're all familiar with one of the big challenges for the West right now is that supply chain is still slowly being rebuilt, and there's progress being made, and the bringing up of Solvay's separation plant is a big step in that. But metallization is still a bottleneck. Magnet manufacturing in Europe or in North America is still a bottleneck. But our goal is to be feeding our mixed rare earth oxides into that supply chain, starting at separation. At that point, the material is atom for atom identical to what will be coming out of a mine. And therefore, the qualification of the material, although it has to be qualified into the separator, into Solvay, we spent a long time qualifying our materials. The downstream magnet that's produced is easier to qualify because at that point, they're atom for atom identical. We're operating at commercial demonstration scale. We have a plant for that separation of magnets that can operate up to 8,000 tons a year. We have a hub that is shipping each quarter. It can process 100 tons per year right now. We are building the next scale up of both of these plants in North America, and we are doing site selection for a European plant as well. ESG, we have done an ISO certified LCA. We did our comparison against primary material. We didn't have enough data to compare this to a short loop. It would be great at some point to do that comparison. But using primary material as our benchmark, there's a almost two-thirds reduction in CO2, 95% reduction in water usage. You know, of course, we're not disturbing anybody's backyard. We're not building a mine in a underdeveloped country. So there's a social impact. And in terms of governance of supply chains for large industry, you know, we are a secure and domestic source for these materials. We do provide material traceability and reporting of the recycling for those of us who are providing us feedstock. So in terms of some of the challenges that we deal with, you know, we've touched on a couple of them, but that diversity of feedstock and be able to handle both different magnet types, because at scale, we believe you can't sort effectively at large scale when devices are coming from end of life. Not even if they were ever well labeled, you can't read most of the labeling any longer. And one of the big challenges right now is that one of the although I think Carlos did mention this, one of the other big competitors for that feedstock, and it's really, to be honest, it's the best for society, is complete reuse of the device, not reuse of the magnet, but reuse of the device. My Tesla battery is dead, or I crashed the Tesla, but the motors are still good. That should go back to reuse to some motor, to some Tesla owner that has a damaged motor. That does make acquiring, feeds, that is one of the competitors for feedstock. Second is that it goes abroad. Carlos also had an image showing that collection schemes of devices means a lot of devices go abroad. They are competing for those other base metal value, which is why we have to recover those metals as well. And then as we sell our products, as I mentioned, that supply chain in Europe and in North America is still weak. So, it's hard to find that entire chain of partners with whom to partner to get the material back into a European automobile maker or a North American automobile maker. And our goal really is to rebuild that whole supply chain. And we're all here in this call because that's important to all of us. It is coming back, but it has a little bit of way to go, and these partnerships are critical to making that happen. We are not trying to do the whole piece. We're not trying to get to magnet manufacturing. We're leaving that to those experts, from separation to metallization and to magnet making. So that's Cyclic Materials. We are building this circular supply chain, working with companies both to help them manage their waste, whether it's from their production or helping them do accounting of the end of life of their devices, whether it's phones or cars. Even if they don't own it, we can give them some accounting of how much we have recycled, and then feeding that back into their supply chain, allowing them to address their Scope 3 emissions. We've heard from one of the auto OEMs, in their analysis of EVs, their biggest Scope 3 emissions came from the battery, but their second biggest came from the motors. And so we're helping address that. Available for any questions. Thank you.
Thanks, Patrick, for a great presentation, but also referencing to the short loop process. And maybe before I go to our last presentation by Lama Itani from Solvay, maybe one question that that were addressed to previous: how you deal with the coatings and contamination in the magnets, because you're also a chemical process, and you don't, how you solve that issue.
Yeah, that's a great question. We recognized early on that in an incoming feed stream that measures in tens of thousands of tons a year, we're going to get all types of magnets. We've kind of talked about all four types: ferrite, which have zero value; neodymium, which is what we all think about as rare earth magnets; samarium cobalt, which has the low value samarium rare earth, but also has cobalt, which is a pay metal; and alnico. And so we have designed our process to be able to handle all four. That means that we do have an exit for cobalt and nickel, and we are selling that down into essentially the battery supply chain, refiners of cobalt and nickel. Our product comes out as a mixed hydroxide product, those two metals together. And then other coatings, whether they are polymers or zinc, we have exits in our hydromet process to be able to remove them. We don't have enough volume for those to become pay metals, as mentioned earlier, but we do have hydromet exits for those contaminants, copper, etc. One of the big challenges in the real world is qualifying your materials, and like any new plant, qualifying with our downstream buyer, Solvay, is painful, but they really held us to very high standards, which we're hitting, and it means that we have learned to get all those contaminants out through other exits, because our hydromet is a recirculating circuit, so we had to have exits to remove them. In that sense, having Solvay as a downstream partner was a great opportunity for us to improve our processes, and we are hitting spec and shipping products to them.
Yeah, thanks. And your product, the mixed rare earth oxide, what is the average purity of that one would be?
It's about 95% pure rare earth oxides. And of course, because we're recycling magnets, primarily just the magnet rare earths.
Yeah. Yeah, thanks for that. Maybe I will take other questions after the session. So I will go to the next speaker. Our next speaker is Lama Ithani from Solvay. You know, Solvay is a well-known company in rare earths, a traditional and historic company processing of rare earth elements into oxide. And Lama has, long have been with Solvay since 2010 with the research and innovation team as an engineer. And Lama, I think January 2023, she joined the Rare Business Unit as a business development manager. And in that role, she take care of customer interactions for the development of REE materials for permanent magnets. Lama, thanks for joining again. And please, have your presentation.
Thank you. Thank you very much, Nabil, for the presentation, and special thanks for IT Raw Materials and Orano for the invitation. I'm very happy to be with you. Can you see my screen? Yeah. Great.
Maybe in the presentation. Oh, okay.
Okay. So I'm the last one to speak. So many of the clever messages have been already said. I will try to focus on Solvay's position in the recycling value chain. And just before going deeply into the topic, a few words about Solvay. So we are a chemical company with 9,000 employees, 45 industrial sites, and 6 major research centers spread in a balanced way in North America, Latin America, Europe, and Asia. So chemical company delivering essential chemical products. It's about soda ash, carbonate, peroxides, silica, and of course rare earth materials that are used in our daily essential application. I can mention air and water purification. I can mention agro, health and well-being, industrial applications, etc. So if we look to rare earth business at Solvay, it started in 1948 with La Société des Terres Rares, and if we look to the separation processes that will be the topic of today, they started in 1956. And over 75 years and in 5 different groups, like Pechiney, Ron Poulenc, Rhodia, Solvay, and recently the new Solvay, this business did not stop to evaluate and to change itself, to propose new products and new processes in order to be aligned with the market changes and the market needs. Again, in the new strategy of Solvay, we are leveraging this history, this know-how and competence in order, of course, to maintain our leadership position in the current markets that are automotive, emission control, electronics, and medical, but to also enter new markets with strategic ambitions like e-mobility, energy transition, hydrogen, and agro markets, and of course for EVs and wind turbine. This is the permanent magnet market, where I will be focusing the rest of the presentation. So where we are in the value chain, so Solvay is rare earth oxide, will be rare earth oxide provider. We are at the middle of the value chain, and our ambition is to contribute to the development of the supply chain of rare earths in Europe. We are reinventing our process and our assets in order to be able to accept large type of rare earth feeds. So we are dealing with feeds from mines outside China, from tailings, and also from end of life magnet recycling. So our strategy is to combine both the version and the recycling supply chain in order to serve permanent magnet e-motors producers and OEMs for EV and wind turbine end markets. This combination is important. I will talk about that later. I will skip this slide. I think Patrick and Carlo showed that very, very good. Maybe what I can just add to what has been said is that, yes, today the overall recycled quantity in Europe is limited to 1%, or 0.5 to 1%, as also said by Patrick. It is limited because everything is in progress. Okay, so the whole value chain is under development in Europe. And when we say the whole value chain, it is from collect to new magnets. Yes, this is the right time to develop all these processes and to be ready for the future. Why? Because in the future, this recycling feedstock or recycling inflow will increase. It will be mainly driven by the increase of end-of-life EVs. Okay, we took some assumption to make these estimations. We took as assumption 12 years, a mean EV lifetime, 25 to 30 year wind turbine lifetime, and a ratio of higher than 80% of collect and recycling level. This is also an important criteria that will impact the estimation. And with that, we see that the inflow coming from EVs and wind turbine will start in 2035. So it is soon, and it could cover up to 10% of European demand. And a significant increase could be expected for 2040 and 2050, where it can cover up to 20 to 50% of the European demand. So very significant. Of course, it is not the whole demand. So that's why in the meantime, and maybe for the future, a combination of the two supply chain, virgin and recycling, should coexist in order to serve the whole demand and towards a real European sovereignty. Okay. Maybe on this slide, a last comment. This graph does not include the swarf and scraps inflow. Okay. And this inflow is also important. It will remain and should increase from 2030 with the all capacity expansion projects in Europe announced. Okay, for permanent magnet production. The magnet production yield will be to monitor in order to estimate the importance of this inflow. Okay, I can go very quickly on this slide because I think still general and we heard many things. 3 ways to bring back recycling feeds in the value chain. Short loop recycling has been brilliantly explained by Carlo and Sohana, so I skip. Let me mention the reuse because it's also another option, even if limited. Okay, it's limited because the magnet, the end-of-life magnet, is injected directly in a new application. So either less demanding application or especially in application where the specification or the performance of the magnet are not changing, which is not the case. Which is not the case of EVs, for example, or wind turbine. And then I will focus on long loop recycling, where the end-of-life magnets will go back to a leaching step before rare earth separation and purification to made completely new rare earth oxide raw materials. Okay. But whatever the route selected for the recycling of end-of-life magnets, collecting, dismantling, sorting, extraction of the magnet, and demagnetization will be a common challenge, let's say, and should be developed in parallel in a competitive way, in some, let's say, incentive also regulations regarding the waste management, regarding how the flow of this waste should be handled within Europe, etc. So this is a point of attention for the development of whatever is the recycling loop. Okay, I know you're tired. This is my longest slide, so try to stay with me. For the long loop recycling, we said that the magnet powder, after collect, dismantling, and making the magnet powder or swarf, will go into a leaching step. So this is what we call hydrometallurgy, okay, step. This part of the process from collect up to the production of a mixture of rare earths, let's say free of iron and boron and free of many impurities by successive selective dissolution and precipitation steps, is led by Solvay's supplier, and we were very happy to announce the collaboration we have with Cyclic on that and on this supply. So I think, Patrick, sorry, I resumed all all the process in a very small box, but there is a lot of know-how, process complexity, and chemistry behind. So Solvay will focus on what we know to do since 70 years, which is rare earth separation. So we get the mixture of rare earths depending on the composition of the rare earths, salt, so could be carbonate, oxide, etc. Depending on the level of impurity and yeah, the composition. A pre-treatment step could be applied before entering the separation process or the separation equipment. The separation equipment is what you are seeing at the bottom right of the slide. Okay, you have what we call a mixer. At this part of the equipment, a organic solvent is mixed with an aqueous solution containing the mixture of rare earths that has been dissolved before entering the separation. Okay, so here we have all the rare earths together, and the solvent will have a specific affinity to one rare earth or to one group of rare earths. Okay. At the settler part, so the end of the equipment, the two phases, organic and aqueous, will be separated, and the rare earth that has been extracted by the solvent will be recovered in the organic phase. Okay. On paper, it seems simple, but to reach the purity which is requested by all the markets we are serving, and also the magnet market, this purity could go up to 99.9% weight of rare earth oxide. This separation step should be repeated several times. To give you an example, to separate two rare earths or two group of rare earths, we have sometimes tens of separation equipment, what we call stages, tens of stages. And I will let you imagine when we have a mixture of rare earths containing 4 rare earths or up to 17 rare earths from mines, the number of stages we have to deal with in order to separate all the rare earths and to purify them from cerium to lutetium, and to extract the neodymium, praseodymium, dysprosium, and terbium for magnets. And this is where we have the added value as Solvay and as experts in this rare earth separation domain. Sorry, I missed just after separation. So we will end with here is just a schematic way to say we will end with pure rare earth in solutions. Okay, pure NdPr salt dissolved, pure dysprosium salt dissolved, etc. That we should transform to oxide. This is a precipitation step. Okay. Which is also tricky and key in order to be sure that we are delivering the oxides in the specifications needed for the magnet market. I tried to compare in an easy way the short loop and the long loop. This comparison is showing that the two processes or the two recycling loop are complementary solutions that should coexist toward a sustainable supply of rare earths in Europe. When the long loop recycling will be, let's say, will be preferred regarding the heterogeneity, the level of oxidation, the level of impurities, and the variation in the composition of the feed, and where also it guarantees the highest performance of the magnet, because we go back to completely new rare earth materials oxide, so raw material. So these are the two differentiating points for the long loop. In the other side, the short loop will be differentiated by the fact that it will have less impact, environmental impact, because by definition, it has less process steps and also less quantities of reactants and water to be consumed. Maybe one point regarding the process complexity, and I think Carlo already mentioned it. It does not depend on metallization, which is a point in Europe today. Missing point, or almost, let's say, missing point in Europe. I say often it does not depend on metallization, because sometimes if we want really to target very high magnet grades, some fresh metals should be injected. Okay. I will keep the cost criteria for debate. Here I put them in the same level, but because it is the cost at the same performance and at the same industrial scale. Okay. To end this comparison, the long loop recycling route will particularly be preferred, as I said, for very heterogeneous feeds, for recreation of the highest quality magnets. The map showed by Carlo was quite let's say easy to catch. And also when the changes in magnet design and composition are required very, very often. For the last slide, or for the conclusions, we all agree that recycling of magnets will contribute or provide security of supply of rare earth for Europe. It give us access to both light rare earth element and heavy rare earth elements, contribute to the preservation of natural resources and also improvement of environmental footprint, and will help to the development of circular economy in this field. However, to reach that, we still have to go through a few challenges. We talked about the feeds availability. We talked also about the development of industrial scale processes going from collect to magnet production in a cost competitive way, and and a way where end users are willing to pay also the development of this chain. Enablers, I think I'm repeating what's said by Carlo, Patrick, and Sorana. Partnership is important. You saw the complexity of the value chain, the complexity of each process at each step of the value chain. So it is not possible other way than partnering at the whole value chain. Regulatory is a challenge, but also an enabler. A challenge today, but could be an enabler tomorrow if we have some European incentive politics, tariff subsidies, and also clearer guidelines for the waste management. That's it for me. Thank you very much for your attention.
Thank you, Lama. Very comprehensive presentation. With your own background in chemistry, Solvay's background in chemistry of the separation, comparing the secondary route as well as the primary one, and benefits of different recycling routes. Maybe we can have a couple of questions, and if the speakers themselves want to provide a perspective on each other's, if Lama or Patrick have some questions to Carlo or Sonara, you can ask and then get a perspective. But before we go that, maybe a couple of questions from the audience. Patrick, especially, there's a question on your process. What exactly is your process? Maybe somebody want to know. And also how you deal with the iron in the magnets. Yeah, so maybe we can start with that, and then from the speakers.
Sure.
Yeah,
absolutely. Now, if I gave too much detail on our processes, I'd have to hire you all, and there are 120 on the call, so we can't hire 120 yet.
Yeah.
But our processes are we have patents pending on them, and therefore we do treat them fairly with a high degree of confidentiality. You're right that about 70% of a neodymium magnet is iron, and that's coming out as goethite on our side. We know that we can use that as landfill cover, as additions into cement, but we are looking for higher value offtakes for that material, given its purity. That said, it's currently planned to use as landfill cover.
Yeah. Can you hear me? Yeah. And any comments from the speakers? Any additional point you want to share?
I think I covered all my thoughts during preparing the slides.
Okay, then maybe a question to Carlo or Sorana. You already answered in the question answer, but the hydrogen decapitation process work on coated or undamaged magnet. We have seen typically one would need to mechanically scratch the coating for hydrogen to penetrate and result in decapitation. So how that works, Carlo?
Well, you've seen in the video that was a hard disk drive magnets that I damaged before. It was cut in half indeed, because then it goes faster, the initiation. Well, first of all, most of the coatings are not tight for hydrogen, which is quite surprising, because they should be against oxygen. But of course, it takes quite a long time. What we do in reality is that we tumble the material, and as said, we not only have magnets, we have a lot of other scrap in, let's say, the material of the hard disk drives or the rotors or whatever. And because of the tumbling, this is creating the damage, and we see that normally all of the material is coming out fully decapitated. So we're not doing any damaging beforehand, because that is introducing additional oxygen. And so far, with what we have seen in upscaling, okay, we are not in full operation yet, but what we've seen, is that no damaging is necessary. If that would be the case, we would do some kind of pre-crunching just before it comes into the HPMS vessel. But that's to be avoided, and so far we're quite confident we don't need it.
Yeah. Thanks, Carlo. Maybe a question to Solveig. Interesting to see the short and long loops have somehow similar cost burdens. I don't know if you agree with that, Lama. And this shows how both are cost competitive, regardless process of complexity. Could you comment further on this, please?
Yeah, the difficult question, because it depends what we are comparing what. So if we are comparing the today existing full Chinese supply chain, we still have some work on. It's not only linked to the process itself. It's linked to the OPEX, let's say, themselves, but it is linked to the CapEx that we have to put in place in order to develop industrially all the processes. It is linked to utilities, energy costs, etc. So if we are comparing to full Chinese supply chain, that's why it's important to work together on a disconnected one for Europe. And if it's the comparison between the two processes, yeah, each process will have its own let's say complexity, OPEX, CapEx, but that's why I said it's a debate, and it is to take into consideration what scale we are talking about, and what performance of the magnet, and what cost.
Yeah, thank you for that.
if I can mention,
Patrick,
yeah.
yes.
Yeah, if I can mention one thought that came to mind that I think none of us mentioned today is one of the the economic challenges of our industries that we're generally working off of a price index from China, which we believe to not be really representative of an equalized market price. It would be great if we could somehow start to build, or successfully build, because we know there are companies that are trying to build it, but a pricing index that is ex-China, maybe only Europe, maybe ex-China across the world. But that is a challenge, I think, for all of us. Whether you're getting the magnets or whether you're just making the raw materials, it's driven by those Chinese index prices.
I couldn't agree more. I would put it even a bit stronger. I think we have a highly distorted market right now, where we're not competing against real prices
You're right.
of China.
Yeah, I also agree with that, and hope we could overcome, with those, Patrick and Carlo. And I think and also a partnership, to overcome this across the value chain, not only, from the processing and rare earth perspective, but also the long commitment from the downstream sector that are present here is also important, and also in alignment that the regulation from different countries, nationalities, and European level is also important. So they are also aligned with the regulations and policies, etc. So I think I'm thankful for all of you, all speakers, Patrick, Sorona, Carlo, and Lama, for joining us, and to continue our discussions. I really welcome all of you be part of this great network, EIT Raw Materials, but also this initiative that I mentioned as SIGN on rare earths and magnets that we are launching in April 9 and 10 in Frankfurt. Please join us. And I also, finally, I thank all the attendees from different companies and organizations. It's great to see you all. And we will continue this webinar series as part of the Magellan project, which is a great project that will have real impact on the Asia supply chain, non-China supply chain, with cost collaboration and so on. So thank you all for joining, and see you next time. Bye.
See you. Thank you very much.
Thank you very much. Bye-bye.
Bye.
Thank you.
Bye.
Bye.
Bye.